Welcome to Elec1, year 2019, question 1. Okay, so first question for question 1, 1A. One type of logic gate is called a NOR gate. And for part 1 it says write down a Boolean expression for the output Q for the 2-input NOR gate in terms of its inputs A and B. Now these are Boolean identities and you do need to know them. And for a NOR gate, the Boolean identity is going to be Q is equal to, we're going to use the plus and a line over the top, and this denotes the NOR gate. Now you can get the mark for this if you use De Morgan's. I know some people might want to use this instead, and so this would also get you the mark. Okay, so 1A2. Draw a circuit symbol for a 3-input NOR gate. Well, the circuit symbol for a 3-input NOR gate is probably what you'd expect. You've got 3 inputs, you've got an OR, but because it's a NOR, you've got the circle on the end. And we're just going to label this A, B, C, and a Q at the end. Right, question 1A3. The first 3 graphs show signals applied to inputs A, B, and C of a 3-input NOR gate. Use the axis provided to sketch the resulting output Q. Now you might be wondering why we've got a truth table here, but the reality is if you want to do this question, the easiest way is to complete the truth table and then use that in order to draw the graph. Now a 3-input NOR gate is very similar to a 2-input NOR gate. That for a 2-input NOR gate, if B nor A are high, then the output is high. So if B is low and A is low, then the output is high. And so for a 3-input NOR gate, it's if C, B, and A are all low, the output is high. And so the output, as far as this truth table is concerned, is 1, 0, 0, 0, 0, 0, 0. Now, what we can now do is use this to create the output for this particular set of inputs. And what we need to do is just go back, look at the graph, and just realize that what we have here is a line where when C, B, and A are all low, Q is high. And this is the only time when Q is high. So when we go back to our graph down here, we know that we're looking for C, B, and A to be low. So when C, B, and A are low, which is here, here, and here, we have a high. And then we scan across to look for any other position where C, B, and A are low. And what we've actually got is a high here. And for all other places, the output is low. Okay, so for B1, now what we have here is a fairly simple logic system, but what we're going to need to do is to use those logic symbols to create our truth table in order to find the output Q. Okay, so the first one that we're going to look at is X. X has a NOT gate and it's linked to B. So what we're looking for is the NOT of B for our answer for X. So all we're going to do is just invert B. So it's going to be 1, 1, 0, 0, 1, 1, 0, 0. For Y, it's the NOT of A. So it's going to be 1, 0, 1, 0, 1, 0, 1, 0. And Z is X and C. So we're going to use the 2 lines, X and C, and therefore Z is going to be 0, 0, 0, 0, 1, 1, 0, 0. And then Q is the OR of Y and Z. So 1 0 1 0 1 1 1 0. Now always check your columns because you actually get the marks for the columns. Make sure that you didn't make any mistakes. My advice maybe is to do this in pencil first, just in case you do make a mistake, because then it does get very, very messy. Okay, so for B2. So B2, we're going to be looking at NAND gates. And what I've got here are the equivalencies for the 3 NAND gates that you need to be aware of. So the NOT gate, the AND gate, and the OR gate. On the right hand side you can see their NAND gate equivalents. Okay, now what we need to do is redraw the original circuit using NAND gates. So the first thing that we're going to do is we're going to label A, B and C because they were the 3 inputs, and then we're going for A, we're going to put a NOT gate. So there's our NOT gate, and then for B we've got to put in a NOT gate as well. And then for the bottom 2, for C and the output from the NOT of B, we've got to put an AND gate. And then finally, from the NOT of A and the AND gate, we need to put an OR gate. And then we've got Q as our output. Now for B3, it says some of these NAND gates are redundant. Cross out all redundant NAND gates. So what we need to do is to look for NOT gates that are in the same line and consecutive. So we have 2 NOT gates which are connected to A. So we're just going to put 1 line through those because that denotes that both of those are paired and they're redundant. And then if we look on the right hand side, the NAND gate connected to C, its output just got 2 NOT gates connected to it, and that is the second pair. And we know we're only looking for 2 because there's only 2 marks, and we show the second pair by giving them 2 lines so that we can see that they're paired and they're not paired with any of the NOT gates above. And then finally, we have a multiplexer. And this multiplexer, the question says, design a circuit that produces the same logic function using a 8-to-1 multiplexer. Now what we have is our truth table on the right hand side. That's just to help us, and what we need to do is just remember that this was the output from the circuit that we had previously, and all we're going to do is just add another column there because these are connected or associated with each of these D inputs. So now we need to draw it. First thing we're going to do is realize that S2 is C, or I'll put that in a different color just so it shows up. S1 is B, S0 is A, because we're going from the most significant to the least significant bit. We need to give a plus volt rail, and we're going to need to give a 0 volt rail. And what we do is we connect a line going up from the 0 volt rail, and we connect a line going down from the plus volt rail. And all we now need to do is to look back at our truth table and look at D0. D0, Q is a high, therefore all we're going to do is go from D0 we're going to go across to the plus. D1 is linked, it has a output of 0 or low. So we're going to link it to the 0 volt rail. D2 is high. D3 is low. Remember to put your dots because you've got lines crossing here. D4, 5 and 6 are all high. And D7 is low. And that completes our multiplexer and question 1.